Okay, so first thing for today, we have some announcements, a couple of new things. This Thursday is going to be our first lecture on probability, and that's going to start us on the next big chapter of the course, which is reasoning under uncertainty, and that's when Jacob's going to take over the lectures. But one thing about that is, you may have already seen this post on Piazza. We have one lecture that's kind of like recap everything in probability you should know from the prereqs, and then a little bit building up some machinery on top of that so that we can move on to the later lectures on Bayes nets. And then really quickly it moves on to some pretty complicated, more general versions of all these rules like Bayes' rule and stuff that you've seen before but maybe not quite in this form. I strongly recommend going through these worksheets that we posted on Piazza, making sure that everything is easy for you at this point, and if that's not the case, then trying to go to one of these sections. The times are posted on Piazza, but it's basically an extra discussion section. They're being held twice a day, today, tomorrow, and Thursday, to go over some of these probability topics in preparation for when we'll need them for lectures starting next week. All right, midterm times. We got our room bookings back to us, and they are not quite what we expected. We requested evening times, as I'm sure a lot of you saw. We got all like early afternoon times, right around noon. And so we realized that this has caused some conflicts that you couldn't have been aware of before because we were saying we'll get evening times. Our previous plan was kind of like a hardline, no makeup, no exceptions policy on this, but in light of that, we're trying to do everything we can to move the times to be a bit later to accommodate everyone who's already told us they have conflicts. But seeing as a lot of you probably have conflicts that you weren't aware of before, we don't want to force you to drop the class or take a hit to your grade or anything like that. So we will work something out with everyone who needs it. And now is not the time to talk about that, but on Piazza, probably sometime later this week, we'll have a better idea of what we're going to do. That said, first midterm is next Monday. 7/11 came pretty quickly, and it's going to be on topics through reinforcement learning, which is what we're talking about today and tomorrow. So you will have one discussion section on reinforcement learning. That's the Wednesday, Thursday of this week. And the homework, I guess I'll skip around on the slide. Homework 3 is going to be released later today, probably tonight. And that'll be on MDPs from last week and RL from this week. It'll be due after the midterm, so you don't have to worry too much about your grade on that until the midterm's out of the way. But seeing as it covers midterm relevant material, you'll want to probably get started on that early and ask questions, make sure that you know how to solve all the problems. And then the last point for announcements is Contest 1 was closed Sunday night, and we got a few submissions. I didn't count exactly how many, but I think we have enough that, or few enough that everyone who submitted is going to be in the top 10, meaning everyone's going to get extra credit. You could have submitted baseline bot and gotten extra credit. I recommend doing something next time. Maybe because I'm saying this, we'll get a few more, so it'll take some minimal amount of effort, but it's like I said last week, not a lot of people playing, so it's still yours for the taking. We're still running matches right now to see whose bot is going to win Contest 1. That'll be done pretty soon, and then we'll compile all the results and present them in lecture tomorrow. All right, so any questions about any of this? Yeah?
What about the next project? Will it be released before the midterm?
Oh, good question. Yeah, the next project, either today or tomorrow most likely, will be released. It will be in time for you to look over it, and if you're ahead on other stuff, work on it before the midterm. That is a valuable way of studying, although make sure, don't put aside like doing practice exams and stuff just to do the project. I think the homework will likely be a bit more helpful than the project for midterm prep. Yeah. Project, okay, so project 2 is due this Friday, project 3 will be due next Friday. Yeah, just every Friday we'll have a project due up until the final, not including the final. Okay, great. So like I said, today we are talking about reinforcement learning. And we saw a bit of a preview yesterday, or not yesterday, on Thursday, at the end of the last MDP lecture, where we had these two slot machines you could play, and you didn't know how likely it was you were going to win on them, and so you had to experiment with them to figure out what's going to do well. Reinforcement learning is a pretty general framework based around MDPs that lets us capture this problem that comes up all over the place, which is, I don't know how to do something well. I have to experiment to figure out what's going to work, and then, based on that, figure out what policy that I want to end up going with. This is different from MDPs, where at the beginning we knew everything about how the environment worked. We were given the transition function, which essentially tells us what the result of every action is going to be, at least up to some probability distribution, and a reward function, which told us how much utility we're going to gain from each individual action we can take. Now we're going to make that a bit harder. And before going into the formalism of it, one thing I want to point out is in reinforcement learning, in terms of how we actually interact with the environment, it's just like this. All we have, this is actually throwing back to a diagram from lecture 2, right at the very beginning, agent and environment interactions, where we have, of course, our agent, and we're trying to program what it's going to do with this. And the agent sends actions to the environment. In the grid world example we've been seeing, that's up, down, left, right. In Pac-Man, it's the same things. And we saw some examples where the actions were not just navigating a maze, there were some other things. And then the environment sends back both an observation, this is what state you're currently in, that's S, and a reward signal that says more or less the same as the reward that we saw in an MDP before, just a positive or negative number to tell the agent that was a good thing or a bad thing that you did. Now, as before, we're trying to maximize expected rewards. And in reinforcement learning, though it's not explicitly a part of the problem formulation, we are, to come up with algorithms to solve them, going to model all of our environments as MDPs in this way. So we saw this one before with the cars where our 3 states were cool, warm, overheated, and if you go fast, you might warm up. If you're warm and you go fast again, you'll lose. You'll get overheated and you're out of the race. But you want to go fast as much as possible to try to go as far down the track as you can. So we've seen this before. And now the difference is going to be we don't know T or R. So we don't know if we're at cool, how likely it is that the fast action will take us to warm. We even don't know if we're at warm, the fact that fast is going to always take us to overheated. When we're starting out, we don't know this. So as a person trying to come up with an algorithm to solve some problem, typically we know what the set of states, the state representation is going to be. And what I mean by that maybe will become clear when we see a couple examples. And we usually know what actions are available to our agent. But these are 2 things that are not totally clear to us, what the model, the transition model, and the reward function should be. So let's look at an example. First is this, oh, he's already walking. Toddler robot. Okay, so what's happening here is, I'm going to pause that actually and talk about it before we let it play. So this is a robot. The bottom of its feet are rounded, kind of cupped like this. And if you put it on an incline, it's just going to passively kind of waddle and end up at the bottom without actually exerting any energy to move motors or anything like that. So by default, it can already perform those motions. What we want it to do now is to figure out with this same set of actions, well, that's not taking any actions, but now we're giving it some actions it can take. We're putting 2 motors in each ankle so that it can turn the feet a little bit. With that extra actuation, we want it now to learn how to walk on flat ground. And so the state representation here, this robot is actually, it's not navigating, it's not looking at what's in front of it and trying to avoid obstacles or anything. It's just trying to learn how to use those motors to get it to move forward. So the state representation is all of the joint angles and joint velocities that are currently part of the robot, and the actions it can take are apply a force on those motors, apply a torque. And so it's using more or less the same kind of algorithms that we're going to talk about today. And it'll slowly learn how to walk forward. So at first, it doesn't really know what's happening, just kind of rocking. And then it starts to figure out, it's not quite going straight forward, but it's figuring out what kinds of waddling and rocking back and forth will get it to actually move. And then in the end, it finally figures out a pretty good policy for how to keep walking. There's an example we're going to come back to that you'll actually implement in your project that's similar in nature. You're trying to teach a simulated robot how to move forward. So just as a quick digression to point out that it doesn't have to be teaching robots how to walk, here's something that you may have seen before. It got quite a bit of press coverage a while back. But this is a similar kind of algorithm, reinforcement learning algorithm, learning how to play Atari games. This particular video is Breakout. So at first, it has trained a little bit, and it doesn't quite know what's going on. It doesn't hit the ball most of the time. And then, well, how long does this go on? Too long. After 2 hours, it's been training, and its reward that it's been given is just, here's the score in the game, try to maximize it. And it plays better than most humans can play this game. But one thing that's cool about this algorithm is it's not done training. You can just let it keep running and running, and it's actually going to get even better than this. So after twice as much training time, it actually figures out this long-term strategy that the best way to get a high score with the least risk of dying, which is going to, of course, make it harder for it to get a high score, which is the only thing it cares about, is to get the ball up behind all the bricks like that. And so, yeah, let's talk about, just real quick, also the state and action representation here. This is a little interesting. We've been working with Pac-Man code where our states were represented as, this is the location where Pac-Man is, and this is the location where all the food are, this is where the ghosts are. But if we hadn't given you that library code, here's Pac-Man, and you can access all the internal state, as humans, all we're looking at is what we can see on the board. And that's actually what this algorithm works with, is the state is just this image. Oh, can I draw? Yeah, it's just this image. And so its policy that it's having to learn is, when I see this, take this action. And the actions are, well, the Atari simulator has like 10 buttons and joystick directions. And so it's just, when it looks like this, move the paddle over. But it doesn't even know that it's trying to move the paddle over. It just presses the left direction on the joystick. So yeah, here's a pretty different scenario that these algorithms also perform really well in. And finally, this is the one that you're actually going to be able to run after doing Project 3. Project 3 will deal with mostly Grid World and Pac-Man, but turns out, exact same algorithm, no modification, will solve the crawler. So what is the crawler? Another robot that's trying to learn how to move. Of course, this one's a bit simpler. It just has two joints, one right here and here, and its states are what angle is this joint and what angle is this joint. That pair of angles, that's the entire state. And the actions it can take are either move this joint this way, or move this joint this way or this way. 4 different actions. And we can see what that looks like when it's running. This one's pretty cute. Oh, hello. Okay, yeah, there's that too. But this is what we're looking for. So at first, doesn't really know what's going on. It's just kind of wiggling back and forth. But it is getting reward every time it moves forward and getting a punishment every time it moves back. So from that, it's trying to figure out how to minimize this pain that it's feeling at every moment. And So this will be kind of painful to just watch and watch it learn how to do this, but if we skip way ahead, and we'll explain what EPS is a bit later, from nothing, it's learned how to move forward. It's a pretty good locomotion strategy. So that's pretty cool. Yeah, we'll learn what, well, you know what gamma is, but we'll learn what epsilon and alpha are by the end of this lecture and come back to this. Gamma, as a reminder, is the discount factor. One thing to note about this is true of all of these tasks we looked at, but it might be easiest to see for the crawler, that in order for the crawler to move according to that great policy it learned at the very end that actually looked like it knew what it was doing, it's not increasing, it's not getting rewards every single time step. It's kind of a long-term plan, sort of long-term, where it has to raise the claw, move this one out, lower it down, and then only as it pulls back with this one is it actually gaining reward. So for a reward signal that it only gets during the moment it's moving forward, it still manages to learn a policy that for most of the time that it's executing this policy, it's not getting immediate reward. So we can see inklings already of this planning and long-term strategies that can come out of even these algorithms that depend only on immediate rewards. So just recap, we looked at what the state and action representations were, and we're trying to figure out how to move through this environment to maximize our reward function. So we've talked already about MDPs, and we're going to start calling that offline planning. The reason it's called offline planning is, well, like I've said a bunch of times now, you're already given the full model, you know everything. But the other thing that's different is all of value iteration, all of policy iteration, those algorithms that we saw before, they depend on running these equations to convergence, which is more or less the same as running a simulation of the environment. And today, now that we can't actually simulate the environment because we don't know how the environment behaves, we have to do something different. In order to learn how the environment works, we have to act in that environment and observe what the results of different kinds of actions are. So you start out, again, knowing nothing. In fact, you don't even know that your actions are north, south, east, west. The agent just has 4 actions that have no associated meaning, and it's going to get a reward, and it can get negative rewards, as this guy is about to, as we go. And so the first idea you might have when I say the problem is we can't run the algorithms we already know because we don't know the model, well, what if we just acted for a long time, tried to build up an approximation to what the model looks like, so an approximate transition function, and since we're treating our rewards as deterministic, we can actually just build up the reward function as well, and then use that to run our old algorithms in the learned model. And this is called model-based learning. So first thing we do is learn an approximate model based on experience, and it'll be easiest to see how exactly we can do that when I go through an example on the next slide. But once we do that, we're going to end up with this function t hat, S-A-S prime, and r hat, S-A-S prime. T hat is, according to all of our observations, our best guess as to the probability distribution over successor states when we take action A from state S. And r hat is going to be what we observed when we made that transition at some point when we were training. And once we have t hat and r hat, well, we can just use value iteration or policy iteration as before. Just replace t and r in those Bellman backup equations with t hat and r hat. And it won't be perfect. It may not be the optimal policy in the true model because there might be some error in the model that you've learned, but it's some approximation. And we're going to have to accept that we might not learn the optimal policy without some infinite number of iterations because there's going to be sampling error. Yeah, so this says count outcomes S prime for each SA. That'll be easy to see on the next slide. And then discover each R SAS prime when we actually experience that transition. So here's an example. Here's our MDP, and we are, in this case, fixing a policy and just trying to use this policy to learn an approximate T and R. So we have to take some actions in order to get these samples, and they have to come from something. In this case, we're just fixing a policy to determine how we're going to get those samples. And say that we get these 4 episodes. So when I say episode, I mean start, act, get to a terminal state, and end. That's one full episode. And this MDP is small enough that the episodes are all just length 3, pretty simple. And how would we actually build up T SAS prime? So T hat SAS prime, rather. Let's first figure out what is TB east C. The way that we would calculate this is look at all of the places where we were in state B and took action east. So that's here and here, and that's it. And in all cases, in this case, we ended up in C. So our approximate model is going to say the probability of that is just 1. And, sorry, T hat. B east D. What's the probability, based on our samples, of ending up in D if we were in B and took action east? 0, right, because we have no samples where that happened, and so that's going to be equal to 0. Now, what about T hat C east D? Okay, so now, again, we need to look at all the samples where this happened and figure out how many of them, or sorry, all the samples where we started in C, took action east, how many of them end up in D? So take just a few seconds to figure that out, figure out what that probability should be. All right, so yeah, let's just shout it out. 75%? I think I heard a 3/4 too. Yeah, exactly. We have 4. This transition happened in all 4 episodes, and that's not surprising, just given the layout here. C is right in the middle. We went east every time. And these 3 times, we ended at D, and this time we ended at A. So that means this is 0.75, and if we were going to do T hat C east A, what would that be? What was that? YC to A? Well, we are going to have to build this up for every SA S prime triple. Every episode what? Yeah, every episode is a sample result. So what I'm doing right now, I'm just picking some particular ones of these values that we'd have to compute and asking what they'd be equal to. And yeah, just to close that question I asked, the answer is 1 minus this result, because our only remaining sample where we started at C, took east, we ended up at A. So 1 out of 4 times. We are going to have to do T hat for every choice of SA and S prime eventually. And this is just, a subset of all those transitions we have to learn. Yeah, question?
C goes north to A, right?
It goes north to A. Yes, good question. Okay, so this is a grid world, which I didn't point out, but you don't necessarily have to know that. In fact, this is kind of the point I was making about the agent, when it's starting out in one of these unknown environments, the actions don't actually have any meaning. So for us looking at this and seeing C east A, when A is clearly north of C, that doesn't make any sense. But in reality, the actual model is that these are actions that can fail, and you can end up going a different direction. From the perspective of the agent, it's just all we have are these samples. Like it doesn't even know, it doesn't have a notion of action failed or anything else. It just has 75% of the time east takes you from C to D, and 25% of the time east takes you from C to A. Yeah?
Then how did it know to never go north?
That was just because for the sake of gathering these particular samples, we fixed this policy. That's all. Yeah? So the question was, how do you determine a sample size? And it's kind of a difficult question to answer, but you can come up with some convergence conditions similar to what we were talking about with value iteration before, where if you collect a whole bunch of samples and your model doesn't change by more than some small epsilon, then you're done. Okay, so these will fill in. Those will be on the slides. For now, they're kind of illegible. But hopefully the idea behind this model-based approach for that grid world is evident. So actually, I want to go back to that real quick. Okay, sorry about this, but the next place we're going to go is it's actually possible to skip this step of learning a model. And as we can see, if we're trying really hard to figure out every single entry in this table of probabilities, that can take a long time, and we can end up learning a lot of information we don't necessarily need to come up with an optimal policy. And in itself, that's going to take some of our computation time, when really what we care about is coming up with a policy. So the next place we're going to go is model-free algorithms for doing the same thing. But before we do that, we're going to see what the difference between a model-based and model-free algorithm is for a much simpler problem. So this problem is just compute the expected age of CS188 students. Well, if we know the actual distribution of CS188 students, if we just know everyone's age, then we can use the normal formula for computing expectation. So that might be that about a third of you are 20, and then a third of you are 19, etc., something like that. But we're now dealing with a situation where we don't know that distribution. And what we're going to do is take samples. So I'm just going to go around. I'm not actually going to do this. I would, if I were doing this in real life, poll just a few people, and based on that, try to come up with an approximation to this actual distribution. So we have n samples, and here's the model-based approach, which for this problem may not seem like the most natural way to do it, but the idea is just, so A in this case could be the probability of being 20 years old. We have n samples, and some number of them out of those n were 20-year-old CS188 students. Based on that, we approximate the probability of a CS188 student being 20 years old. And then once we have this for every age that a CS188 student could be, we have our approximate model, where our model is just this probability distribution. And so we can use the normal formula for computing it. Why does this work? Because you eventually learn the right model. If you take enough samples, these PAs will converge to what they should be. Now over here is the model-free approach, which may be what you had in mind first as a way to solve this problem, which is just do this, take the average. And it's important to notice how these are different right now. Over here, we're not explicitly writing down what the probability of each age is and then using that to compute an expectation. We're just using some kind of sample average. And the reason this is going to work is if we take a whole bunch of samples from a population of people who are mostly 20 years old, most of the samples are going to be 20-year-olds. And more generally, the probability that we get a sample is going to be equal to the probability of that outcome from the original population. And this is implicitly keeping track of these probabilities. And you can notice, actually, if we plug this in right here, it turns out to just be the same expression. The difference is we're cutting out this intermediate step. And that's what we're going to do with model-based reinforcement learning, or sorry, model-free reinforcement learning algorithms. So let's start looking at that. The first class of these we're going to look at is passive reinforcement learning. So from this, we're not trying to actually come up with an optimal policy. We're just trying to basically run policy evaluation. For some already fixed policy, how well is this going to perform? And normally the way this is done is you actually have the agent acting out this policy in the environment, and then you work with that. Here in this animation, another way that is just as reasonable to think about it is it's kind of like your agent has no control over what's happening and is just watching a video of itself performing in the environment and learning based on that what it really how well that policy performed. So here's the passive reinforcement learning problem. The task is simplified. We're just evaluating, no longer coming up with a policy, not yet anyway. We fix a policy, and again, we don't know these pieces of the environment, and we just want to learn the state values. As a quick recap, we're trying to learn v pi s, this value function we talked about last week, for every state, and that corresponds to if I act according to this policy pi, what is my expected reward, sorry, my expected sum of discounted rewards starting from state S. And yeah, this is what's important, is there's no choice about what actions to take. You just execute the policy and learn from experience. That said, it's not offline. You are still actually taking these actions in the environment. So here's the first idea, direct evaluation. And the way this is going to work is essentially same as before. We take some number of samples, and a sample is an entire episode where you start, walk around for a while, end up at a terminal state, and then exit. That's one full episode. And the way that we're going to use that to approximate V is, well, if, here, I won't even write anything down. If in 3 of those episodes we visited, or we started from state C, and then the sum of discounted rewards that we got in those 3 episodes were 1, 2, and 3, average those. And then the value for state C is just 2, because that's the average of 1, 2, and 3. It's called direct evaluation, and again, this is something that's a bit easier to see with an example, so we'll just jump right to that. Same exact grid world, MDP, only now we don't necessarily know, or we do not know, the transitions and rewards. And again, we're fixing a policy. So these are the episodes we observe, and we need to fill in values over here. And remember, that's going to be some assignment of numbers to each of these states. So first, let me point out gamma is 1. We're not discounting in this example. So to compute the value at A, right here, we need to look at all of the samples where we visited A. That's this one right here, and that's actually the only one. This is the only sample where we visited A. And the sum of discounted returns after being at A from following this policy in that one example was 10. So with only one sample, the average is just equal to that sample. Sorry, that's minus 10. And then now we look at D, do the same process. This time there are 3 episodes where we went to D. And in all 3 of them, the sum of discounted returns moving forward from D was 10, plus 10. So that value is plus 10. Now it gets a little bit different. Let's jump to E. Yeah. No, let's do C. C is a better example. So C appears in all 4 episodes. And of course, we fixed the policy already. So we took action east at all of them. But now we want to figure out what the value of C is according to this estimate, this direct evaluation. And the way we're going to do that is look at each of these. The sum of discounted rewards moving forward from C in episode 1 was minus 1 plus 10. Our immediate reward from where we were was minus 1, and then we got plus 10 on exiting. So that's going to be equal to 9. And then it's 9 again right here for the same reason, 9 and minus 11, because we get minus 1 for the transition from C to A, and then minus 10 when we exit. So to figure out what the value at C is, we just average these four numbers. And what do we get? 4. Yeah. 9 plus 9 plus 9 minus 11. 16 over 4 is 4. So the value at C is 4. And I'm not going to do this for the rest of the states, but it turns out when you do these, it works out like this. And it'll fill in the rest of them in a second, but I've already written them there. So I will leave that out for a moment. Now, one thing I want you to notice is when we are talking about doing this for B or E, which we didn't go through by hand, but these two episodes are the ones where we have B. And the sum of discounted returns from both of them is 8. So we say the expected return, or the value at B is 8. And then similar process for E. But there's something a little strange about this, because notice that from E, action north, we end up at C, and B, action east, we end up at C both times. And both times, we got the same immediate reward, -1. Also note that then we are at C. Because of this Markov property, it doesn't matter how we got there. We should expect that if we go from B to C and get a reward of -1, and then get whatever the value of C is, we should get the exact same value as if we go from E to C, get the -1 reward, and then are at C. Yeah, question? Okay, so 9, 9, 9, -11, those came from -110, -110, -110, -1, -10. And then 4 is just the average of those numbers. 8 came, okay, yeah. So let me scratch these out. 8 came from looking again at these two episodes. It's getting a little messy, sorry about that. These are the two where we started at B. And the reward going forward from B, since we're not discounting, was just -1, -110, 8, -1, -110, 8. And then we're not looking at the other two episodes because we don't start at B there. Yeah. Yeah, exactly. So this is going to converge eventually to the right values if we just have infinitely many samples. It'll eventually get there. But there's some structure coming from the fact that this is a Markov decision process that we're not exploiting here. We should expect that this value and this value are the same. Or given they can take, maybe a priori we don't know that you get -1 reward moving from those two, but it's strange that once we find out that you get -1 from here and -1 from here, and then you end up at the same state, they're different things. That's coming from the fact that this one time that we failed in our east action and ended up at A, which is a bad state, and got -10, happened to be a time that we started at E. But maybe a smarter algorithm would notice that that should be affecting B and E in the same exact way, because that only happened at C, which can happen after being at either of those places. Oh, yeah, fill those in. So, yeah, that's our problem. What's good about it, first of all, is once you figure out where all those numbers come from, it's just simple averaging. So it turns out to be a very easy to implement algorithm. And again, we're going to require this of all our algorithms today, but now we've seen at least one that works where we can figure out the values without knowledge of T or R. What's bad about it? It wastes that information about state connections. And we're not going to be able to do something like what we did with value iteration, where once we know the value for C, B and E just directly follow as the immediate return or reward going from B to C plus the discounted future rewards. And then same thing for E. We're not using that here. Not at all. It's just yeah, basically using completely separate information to train each of these states. So why not use policy evaluation? We talked about policy evaluation before as basically simpler value iteration, where rather than taking a max over actions, we fixed our actions. Can we do some kind of algorithm like that here? Well, let's at least try and see what happens. So each round, replace V with a one-step look-ahead layer over V. What does that mean? Well, from before, we know, start with our depth limited at depth 0 estimates of reward equal to 0, because if you take no steps, you can't get any reward. And then recursively, just like before, build upward. Our time-limited values at depth 1 are going to depend on those at depth 0. Time-limited values depth 2 depend on those at 1, etc. Of course, the problem is we need T and R, but is there some way that we can use this idea, this update to V, without knowing T and R? Can we take a weighted average without knowing the weights? You might be thinking back to that CS188 age example, where we could come up with an approximate model, this T hat, and then weight everything this way. Or we could just take a lot of samples of this value right here, and it may not be clear yet how we do that, but take a lot of samples of this value right here, and then since they're coming from this distribution, according to this, if we just take the average, then it will converge to the same thing as if we were to do it the model-based way, where we were actually learning a function T. So what would sample-based policy evaluation look like? This is coming in the wrong order. Okay. We want to improve our estimate of V by computing these averages. So take samples of the outcomes S prime by doing the action and average. So we're sampling S prime from actually acting in the environment, and then we're going to compute this value. And again, this R S pi S S prime, another thing we don't know, but that we get when interacting with the environment. We get where you ended up and the reward you got. And we don't quite know these yet, but just suppose for a moment that we do. Then that looks like this. Oh, come back. Take a bunch of samples. Oh, man. Sorry. And then when you have n samples, just back it up like that. So this now is, we could do a value iteration like algorithm where we do depth limited 0 and then take a whole bunch of samples according to that depth limited at 0 V0 and use this equation right here to get V1 and then repeat. Take a whole bunch more samples and use these again and do that over and over and over again, and then we'd have an algorithm. This is basically policy evaluation, but based on samples instead of the actual transition function T. The problem is we can't guarantee that we're going to be able to start from any particular state S. Remember that we're actually acting in the environment, and if we're in a maze that looks like this, and here I'll use Pac-Man for this example. We want to figure out, basically gather a whole bunch of samples of what happens when you take a particular action from S. Well, you have to actually get to S first in the actual environment before you can get a single one of those samples. And so unless you have this magical power to either simulate the environment fully, in which case we're not really doing reinforcement learning in the first place, or reset to any state that you want, which sometimes we can do, but we won't deal with that for today, then this isn't going to work for us. So rather than only try to gather samples for this particular transition we're trying to learn about right now, here's the big idea. For temporal difference learning, we're going to act in the environment, and we're going to get a bunch of experiences for every action we take, every transition, and we're just going to use all of them as we go to update VS for whichever state we just left. And because we're sampling from the actual transition model by taking an action in the environment, the likely outcomes will contribute updates more often, and that will lead to that convergence that we want. So Policy is still fixed. We're still doing evaluation. But once we take a bunch of samples, here's what one sample looks like. Our update looks like this. So what's happening here is we have some existing estimate, V pi s, based on all our samples so far. When we get one more sample that we were at S, we took the action that our policy tells us to take, and then we experienced some reward and successor state result of that. We call that sample. Compute this based on, again, still our existing estimate of V pi, but at S prime. And now we're going to take this weighted average of V pi and sample. And it's based on 1 minus alpha plus alpha. 1 minus alpha times V pi plus alpha times sample. This is going to be a parameter that we have to tweak, and exactly how to do that is something we'll address a little bit later. But the idea is we are taking, again, we're accounting for the new evidence in some way. And in fact, I think it's actually a little easier to talk about in this other form. So just notice really quickly that going from that second line to the third line, that's just a little bit of algebraic manipulation. They're actually the exact same thing. But now, what is this difference? Our sample is what we actually experienced in the environment this time as the value of our current state. And V pi is our existing estimate. So this difference, sample minus V pi, if that's positive, that means during this experience, we did better than we thought we would. And so that sample is bigger than V pi. So this is a positive amount. And so we end up shifting up our estimate of V pi. If sample is less than V pi, we did worse than we thought we should. And so this is a negative amount right here. And then we're going to lower our estimate of V pi. So at least the direction that it moves when these two things happen should be kind of intuitive. If we did better than we expected, shift our estimates up. If we did worse than we expected we would, shift our estimates down. But what exactly mathematically is going on with this alpha? It's not exactly taking an average of all of the samples we've seen so far. In fact, what's happening is we're taking an exponential moving average. So what does that mean? When we do one update of xn, xn is our moving average, then it's going to make recent samples more important. So if we unpack this recursive definition of x bar n like that into all of the actual samples, xn, xn minus 1 down to x1, then you'll notice that the most recent sample, xn, has no coefficient. Alpha is going to be something between 0 and 1, and so 1 minus alpha times this is going to make this smaller. 1 minus alpha squared is going to be even smaller, etc. The farther we go back in our memory of all the experiences that we've had, the more we're going to essentially discount that experience. We're not counting it as being as relevant. And the reasons for that are here, just basically that the most recent transitions are most reflective of your current estimates of everything. Because remember, these estimates back here, they depended on your early estimates of V pi, which were not so good. And as they get newer and newer, they depend on more accurate estimates. And so xn should be the most accurate, xn minus 1 should be the second most accurate, etc. And as we take more and more samples, that will converge even faster than if we were doing an arithmetic mean of all of these samples. And decreasing learning rate can give converging averages. We're not going to talk about the exact theoretical underpinnings here in really any depth, but in most of the examples we're going to see, we're going to use alpha equal to 1 over n. So that's something that's going to decay as we go. We're going to become more reliant on our existing estimates, but not too much faster than that. We're not going to do alpha equal to 1 over n squared. And there are some reasons why one of those works and the other doesn't, beyond the scope of the class. We're going to stick with this. So let's do another example here. Yeah, so first of all, that 8, I just filled it in so that we can get to the more interesting part of this example. Don't worry about where the 8 came from. You can imagine we're partway through running the algorithm already. So we first observe this transition. So yeah, we start out in that leftmost square. We take the action east because that's what the policy we're trying to evaluate tells us to do. And then we end up in C right here with reward -2. So we're going to use this backup equation. And this is just from that previous slide where our existing estimate, V pi, we're estimating for B. That's just 0. So let's actually plug that in. 1 minus alpha times 0 plus alpha times. So what is r s pi s s prime? That comes from the experience we just had right up here. The experience reward was -2. So that's what goes there. And then plus gamma is just 1, so we'll leave gamma out. Plus this existing estimate V pi at S prime, our successor state C where we ended up. Actually, I should be circling there. When we do that, we get 0, and alpha is 1/2. That's just what we've set it to for the sake of this example. So this is going to be equal to -1. And that's what we end up with there. So we take one more transition, and I'm going to erase that to make room for the other one. And from C, we again take action east. And our experience is you end up at D, and you get reward -2. So if we do that again, it's 1 minus alpha, which is 1/2. V pi s, our current state, which is C, that's just 0. Plus alpha, 1/2. The reward we just experienced, -2. Plus gamma, which is 1, times V pi at our successor state. So the successor state where we ended up was D, and we already have an existing estimate there. It's 8. So 8 goes there, and then what is this equal to? -2 plus 8, 6. Half of that is 3. So our new estimate for the value at C is 3. And you do this with a lot more samples than just that, but hopefully going through with one episode there from B to D illustrates the point a little bit. So problems with TD value learning. Well, the biggest problem right now for us is it doesn't actually tell us how to extract a policy from any of this. Because before, value iteration was an algorithm that we could use to come up with a policy, because we had this, where we could do one more step of computing that was, we called this policy extraction, one step that you do at the end of value iteration. One step look ahead according to the transition and reward of which action from each state is going to do best for you based on your really good estimates of V, and then from that come up with a policy. We can't do that anymore because this depends on T and on R, things that once again we don't have. So TD value learning gives us values. It gives us estimates of how well one policy is going to perform, but it gives us no way to come up with a better policy than the one we were just dealing with. So what's a potential fix here? What we really want are these Q values. If we had the Q values, then we'd only have to take a max over all the different actions we could take, rather than do this extra step of computation that depends on information we don't have, and then do a max over those. So that's going to be our next step, is improve this algorithm in some way so that it's not just learning values, but it's actually learning Q values. And then it is going to make action selection model free as well. So that was passive reinforcement learning, where we were talking about, here's a policy, follow it, see how well you do. Now, we're talking about active reinforcement learning, where the agent actually has to decide what actions to take in order to learn the policy. And we'll talk about some metrics for learning quickly and learning well tomorrow. For right now, we just want to, in some intuitive sense, try to figure out all the right Q values. And then once we have those, it's easy to extract the policy. So one quick note about this. Remember, when we look at this picture over and over again, the agent starts out not having any idea what the actions do. And in fact, if north is this direction, and this agent just took the action north and it failed, because that can happen in grid world, then at least at this point, to the best of this agent's knowledge, action north throws you into lava. Never take that action. It's a bad action. It's going to have to take more samples, and in particular, take more samples where it chooses the action north, even though it's already decided that it's bad, before it's going to figure out, wait, no, that was just one unfortunate consequence of randomness, rather than what always is going to happen. That's that theme of exploration that we saw before coming up again. Before we get to that, let's actually talk about this algorithm where we're going to try to learn all of the Q values. So this all is the same except for this line right here. Rather than a fixed policy that the agent's going to follow, we are now, or the agent is now choosing the actions. So the learner makes choices, and it's going to have to make this trade-off, exploration versus exploitation. Exploration means take actions that don't necessarily look really good to learn more. Exploitation is just the opposite of that. Take actions that, according to what you've learned so far, look really good so that you can get as much reward right now as possible. We're going to have to balance that somehow. So we've seen this before, actually, where here's value iteration. And when we were first looking at the Bellman equations, and I said, all right, so here's the Q values in terms of V. How do we fix this to be a recursive formula for V's? And we came up with this equation. I also said, can we fix it in some way to come up with a recursive formula for Q's? So V doesn't appear anywhere. It's just Q in terms of other Q values. And we came up with this. So in this equation, just as a recap of what we did sometime last week, we are trying to perform a backup, a depth limited by one more increased depth estimate of this Q value right here. So we are going to take an average over all the possible successor states. This is assuming now for a moment that we know the model. This is what it's actually equal to. Of our reward, again according to this recursive idea, where our reward is just going to be immediate reward from one step plus our discounted expected future rewards here. Now, we're talking about expected future rewards for acting optimally. So equivalently to VKS, because S prime is equal to the max over actions available of Q K S prime A prime. That's just by definition. And my choice of A prime there is just because the name A is already used for this action. Those two are equal, so we can just plug that in right here, and we get this new formula that is Q in terms of those things. So we did a little more detailed derivation of this last week if you want to go through that video and see that again. But for now, I just wanted to remind everyone of this, which we saw earlier, because that's what motivates the algorithm that we're going to finally settle on, Q learning. So just like TD learning was sample-based value iteration, this is sample-based Q value iteration. Really all we're changing is we're using that second formula over the first one, and that allows us to not behave according to one policy. So here's that equation again. This is just from the previous slide. And we're going to learn the Q SA values as we go. We'll see a demo in a minute that is that over and over, but here's the way the algorithm runs. You take an action in the environment. How you choose an action we haven't exactly specified yet, but for now just take some action, and you get a sample, which is you were at this state, you took this action, you ended up at this state, and you got this reward. So that's SAS prime R. And then we have our old estimate, Q of SA, and we have a new sample estimate that's based on just pulling this expression out of this formula. And then we're going to once again get an exponential moving average. This sample we just got now is based on our most accurate, because they're most recent, estimates of the Q values. So we want to weight it higher. And just like before with TD learning, we had our values. We just put Q where it said V before, and we have Q learning. So what this means now is we can get these samples, since we're trying to maximize overall Q values, we can take this according to any action, not according to a particular policy. We'll ultimately learn the right Q values, and even though we might have been acting suboptimally the whole time, we'll end up learning the right policy. So let's see what that looks like. Yeah, great. So here's grid world again. The numbers are unfortunately a bit smaller. If you can't see the numbers, at the very least they will start to turn green and red when they get good and bad. So right now I'm just controlling it, because we haven't talked about action selection yet during Q learning. So I'm just controlling it according to the keyboard, and we're using a simplified version of the environment where 1, no discounting, and 2, no action noise. So all the transitions are deterministic. I can just go back and forth between those states as much as I want and be successful. Notice that nothing has happened yet. We just have zeros everywhere. We are actually performing those updates that were on that slide. Every time I make a move, it's just that everything everywhere is currently 0. And in this environment, we only get rewards on exiting. So let's actually exit and put something here so something interesting can start happening. When I exit from here, as a recap, because we've seen this particular grid world environment a bunch of times, I'm going to get a reward of 1. And so what does that mean for my Q value update? Well, I'm going to use alpha equal to 1/2, because 1/2 tends to make it easiest to see what's happening. And so when I exit, it's going to take the average of its existing estimate, 0, and the value that it just got, which was 1, and that's 50. If I go up there again, first notice that when I step that way, because it's using the Q value estimates and not just the immediate rewards that we get, it just updated that top right square that is not a reward square to be the average of 0 and 0.5. Now it's 0.25. And if I exit again, the average of 0.5 and 1, that just went up to 0.75. You can already see if I do this a bunch of times over and over and over, eventually that will converge all the way up to 1, which is its true Q value. And those rewards that are coming from exiting that way are going to propagate back all the way to the start. So I'll do that a few times. And hopefully you can see those numbers, but if not, it's starting to get a little bit green. And right now, I'm following basically the same policy over and over and over to fill in these values. But again, this doesn't depend on us taking those actions every time. In fact, we are interested in the possibility of other actions being better than the ones I'm considering. So what happens if I step left? Well, our max Q value at the state I just moved into was 0.93. And so that estimate right there just got the average of its existing 1, 0, and the one of where it stepped, 0.93, up to 0.46. So if I just start moving around, notice that I'm not actually going to that 1 anymore. I'm just kind of taking a bunch of actions, and the screen is going around everywhere. Let's put some red in here. So same thing is going to happen there. Average of 0 and minus 1 is minus 0.5. And now that'll start propagating backwards. Now we have something red there, but notice every time I step from right here to the right, nothing's turning red there. We don't have a negative Q value right here. And why is that? So yeah, let's get some interaction. Yeah. Yeah, exactly. We're taking the max over the Q values of the successor. So from over here, yes, we do have one action that's going to give us minus 0.94, but of course, if we were acting optimally, we would never choose that action. We'd choose one of these other ones that gives us 0. And so that's the value that's used for this Q update. And now, in fact, if I start moving back, it recognizes the possibility that I can move up to here, and we see, again, more stuff filling up in there. Okay. So here's another demo. And this one, it's a little bit flashy, so brace your eyes. But this is the crawler again, and something a little interesting is happening here, where as before, we can see the crawler acting and trying to learn up there, but we got something going on down here. Can anyone guess what this is? What was that? Yeah, this is a way of representing the actions it can take. And to be more concrete, actually, we are using a 2-axis grid here, where these actions correspond to one of the joints, and going up is retracting that joint, and going down is expanding it. And then this axis is the other joint. And so since it can basically move that according to some ticks in either direction like this, when we represent the state space in this way, its actions are just move in one direction in this grid. And that's the same as move your joint in one direction. With that in mind, we actually see that these are the V values. Green is better, red is worse, of being in each state. And these are the Q values, where of the 4 actions that you can take from any of these states, we're going to learn different Q values for each of those actions. And that's why it's split up into quarters here. Now, it gets kind of boring as before if we just watch it, but if we skip a million steps, let it train a lot without us watching, then now it's just from acting more or less randomly as it has been, it's learned the optimal V value just by taking the max of all the Qs, and the optimal Q function. Again, we're going to cover epsilon in a second, but for now, epsilon 0 just means it's going to stop exploring, and this is the policy that it's learned. It's interesting to watch the trajectory that it's following in this representation of the state space, where from each of these states, the best Q value is following this loop right here, and then that's the policy that it's learned. If we can't actually force it to do this explicitly, but if we can kind of get it into some other part of the state space, then we can see other parts of the policy that it's learned, because it will have some optimal action assigned to every state, but yeah, it's too random. We don't want to wait around for that to happen. Okay, so any questions about either of those demos? I can pull up the other one too if we want to look at that again. It's probably easier to see Q learning happening there than it is here. But about how these updates are working, why we're getting the numbers that we are seeing. Any questions? All right, well, in that case, look forward to being able to run both of those, because your Project 3 code will do exactly that, which is kind of exciting. All right, so Q learning. Some properties. I mentioned that even if we're just randomly acting, and we saw this with the crawler, acting more or less randomly completely suboptimally, then we'll still learn the true Q values. It'll converge to the actual Q values, which gives us the optimal policy by just taking the argmax of all the Q values for each state. And just as a quick point of vocab here, we call this off-policy learning because we don't have a fixed policy that we're following. And in particular, we learned that policy without following it. So off-policy learning. Caveats, of course, you have to explore enough. The intermediate estimates of that were not very good. And when I say explore enough, that's not just when we were doing grid world, and the first several I did was to go up and right over and over and over because I knew that was a good policy. If it turned out that I took some really weird, convoluted path to get there, and then we got positive rewards along that path and didn't continue looking at alternatives, then I would just be stuck in this local optimum, which we don't like. And so exploration is still important. And you do have to decay the learning rate as you go. Otherwise, your values won't converge. And yeah, you can imagine if something happens one way every even iteration and one way every odd iteration, or in every even state or odd state, something like that, then if your alpha is too big, it'll just keep bouncing back and forth between those two values and never converge on some average between them. So that's also important. And not decrease it too quickly. There are more general conditions, but as before, this is always our safe choice of alpha for now. And now we address this question, which I've been mentioning over and over, but not giving you an explicit algorithm or some explicit way to deal with this. What's happening in this picture? Well, the usual place. If you go one place and get one same thing every time you go there, you never eat dinner anywhere other than Laval's, and you never get anything other than the Laval's special. And then the new place opens up across the place. I don't remember the little cul-de-sac thing. Now you have the Daily Pine over here that opened up a couple years ago. Do you want to go try that out? Well, you know, Laval's is safe. You know that Laval's pizza is good, and so maybe you just never bother going over there. And turns out this is actually the policy I've followed. Laval's is safe. I've only been to the Daily Pine a couple times, don't remember what their food's like, so I haven't been exploring very well. But maybe it's the best food in the world, and maybe I really need to try it. And that's kind of a silly example, but it's the same kind of reasoning we're dealing with here, where it's a bit more abstract here. There might be another Q value that appears suboptimal now, but is actually better for some reason we haven't seen yet. How are we going to make sure that we find out that's the case, if it actually is? Here's the simplest scheme. It's called epsilon greedy. The simplest version of epsilon greedy is if epsilon is 0, then it's just greedy. And greedy means you have current estimates of Q values. Just act according to the optimal policy that you get from your current estimates of Q values. So basically, if you take one action from one state and something bad happens, you're probably never going to go that way again. If you take one action from your start state and something good happens, you're going to go that way forever. That would be epsilon 0 greedy. Now as we allow epsilon to be something higher, say 0.5, then half of the time we're going to act greedily in that sense, move according to the best Q value for any of our actions, and the other half of the time just choose some completely random action. And when we do that, we will ultimately end up exploring every outcome in the limit. As we take more and more and more samples, most of our experience will be happening along the trajectories preferred by our policy, our greedy policy that we follow half of the time. But we will still now and again try out some other stuff to see if it works out well for us. What's the problem with totally random actions? Well, I didn't say this before, but the crawler was using epsilon greedy, and it's initialized to 0.8. And so if we're using random actions and we learn the best policy, then this is what happens. So skip a million iterations. Okay, so now it's more or less learned all the right Q values, and it's still acting randomly. Epsilon's still 0.8. 0.8 of the time, it chooses a random action rather than the best one. It's learned all this stuff, and it's not really using it at all. Not until we bring epsilon down. It doesn't have to be 0 for it to be visible. Even at 0.1, it's more or less following the policy we want it to, the policy it's learned. But the point is, taking random actions is kind of the opposite extreme. You just thrash around in the environment without exploiting any of the knowledge that you've gained. So one solution, which I just kind of did by hand, is to lower epsilon over time. And another solution is exploration functions. So exploration functions are basically a more principled way of trying to make sure you look at all of the state space, even parts that at first glance don't seem so promising. So random actions is one exploration strategy. Instead of that, we can explicitly choose to prefer actions that take us to places we haven't been before. That looks kind of like that. So how do we do this? We're going to look at just one example, which is we're going to take a value estimate U. So our value estimate, of course, is the Q value that we've learned so far. Something like that. We'll see this in context in a second. And also a count, N, of how many times we've visited a particular state or a particular state action pair, Q state. And then we're going to, instead of just using the Q values as the function that determines our policy, we're also going to give it this bonus right here of plus K over N. So K is just some fixed constant, but when you haven't visited a state at all, when N is 0, this is infinity. And you can come up with other implementations where it's just something big, but that means just always at the very beginning, choose to go somewhere you haven't been before. And then when this is 1, that goes down to K. When it's 2, it's K over 2, etc. The more times you see this state, the less of that reward you factor in, until when you've been there a million times, this essentially just goes to 0, and you're left with just the Q value. When you're done training, you'll have been to every state a million times, and so you'll still end up with just the optimal Q values and the optimal policy, but you'll have a more principled exploration strategy. So here's a regular Q update. All we're doing now is adding in this exploration function, where instead of just updating Q values, we are going to update according to Q values plus that bonus, and then these are also the values that we will use to determine a greedy policy. So if a policy looks greedy with respect to this function, then it's going to be choosing whatever, at every action choice it can make, it's going to choose whichever action immediately maximizes this quantity. But since not only does this account for, in your successor state, how many times have you been there before, this is also, because we're backing it up in this way, the same property Q has, it's the discounted sum of all future Q values. This is also this behavior is going to happen here too, where if somewhere far down the line in some direction there's a state that you've never visited, then that's going to get backed up until you see that if I take this action now and then that action next, eventually I will end up in a state I haven't explored before. So point is, this discounted consideration of all futures is also happening to this term. And we get, by following a policy that looks greedy with respect to this other function, we get behavior that encourages exploration of the entire space. So here's the story so far, MDPs and RL. That's more just for reference when you're coming back as the recap of everything that we've seen. Tomorrow we're going to cover more about reinforcement learning, defining regret, and some other things that we haven't quite touched on how to improve these algorithms.